Our universe is expanding, and with it, so is our list of cosmic puzzles. You are about to journey through 25 of its most profound mysteries, from the invisible grip of dark matter to the force tearing space-time itself apart. This exploration will fundamentally challenge what you think you know about reality. Why does the cosmos appear fine-tuned for life, yet seems so utterly empty? What is the true, ultimate fate of everything? Which of these cosmic riddles do you find the most compelling galaxies should be flying apart? When we observe the immense speed of stars orbiting on the outer edges of spiral galaxies, the math simply does not add up. There is not enough visible matter, not enough stars and gas to generate the gravity needed to hold these cosmic islands together. They should have spun themselves into disarray eons ago. The only explanation is that they are caught in the gravitational web of something we cannot see, a mysterious substance that binds the cosmos, dark matter. We can map its invisible presence through other ghostly effects, like gravitational lensing, where the fabric of spacetime is warped by unseen mass, bending the light from distant galaxies into faint, beautiful arcs. This shadowy component is not a minor player. It constitutes roughly 27% of the entire universe, more than 5 times the amount of all the ordinary matter we know and love. So what is it? The leading candidates are as elusive as their effects. Some physicists propose WIMP, weakly interacting massive particles, heavy entities that barely interact with normal matter. Others suggest actions, incredibly light particles that could flood the cosmos. To catch them, scientists have built exquisitely sensitive detectors in deep underground laboratories, shielded from cosmic rays by a mile of rock, all waiting for the telltale ping of a dark matter particle collision. Yet, after decades of searching, the detectors remain silent. We are surrounded by an ocean of darkness, feeling its pull in the motion of every galaxy, yet we still cannot grasp what it is made of. This fundamental ignorance stands as one of the most profound and humbling puzzles in all of modern physics. But if dark matter's gravity pulls the universe together, a far more dominant force is doing the exact opposite, pushing it apart. In the late 1990s, 2 independent teams of astronomers made a shocking discovery. They were measuring the distances to far-off supernova, expecting to confirm that the universe's expansion was slowing down due to gravity. Instead, they found the expansion was speeding up. It was as if you threw a ball into the air, and instead of falling back down, it shot away from you faster and faster. This cosmic acceleration demanded an explanation, a mysterious repulsive force that was named dark energy. This is not just another component of the cosmos, it is the main component, constituting a staggering 68% of the universe's total energy budget. Think of the cosmos as a vast ocean. Dark energy is like a strange current flowing through that ocean, causing the very space between galaxies to stretch. Not because galaxies are moving through space, but because the fabric of spacetime itself is expanding. The leading candidate for this force is something known as the cosmological constant, an inherent property of empty space itself. Even in a perfect vacuum, according to quantum physics, virtual particles flicker in and out of existence, and this seething energy of nothingness could be generating the repulsive push. Yet the calculated energy from this quantum vacuum is astronomically stronger than what we observe, off by a factor of 1 followed by 120 zeros. This is perhaps the worst theoretical prediction in the entire history of science. Another idea is that dark energy is not a constant at all, but a dynamic field that has changed over time, a concept called quintessence. This would mean the strength of this repulsive force could evolve, leading to different possible futures for our universe. And that leads to the ultimate question: what fate does dark energy dictate for all of existence? If the acceleration continues at its current rate, the most likely outcome is a heat death, a cold, lonely end where the universe expands forever. galaxies drift beyond the cosmic horizon, stars burn out, and all activity grinds to a halt in a state of maximum entropy. But if dark energy intensifies over time, a more dramatic and terrifying end awaits: the Big Rip. In this scenario, the repulsive force would eventually overcome all other forces, first tearing apart galaxy clusters, then galaxies themselves, then stars and planets, and finally, it would rip apart atoms and the very fabric of spacetime. The nature of dark energy does not just shape the cosmos today, it holds the key to the final chapter of everything. This relentless expansion finds its origin in the universe's very first moments. To solve several profound puzzles, scientists proposed a breathtaking idea called cosmic inflation. This was not the steady expansion we see today, but a period of unimaginably violent, exponential growth that occurred in the tiniest fraction of a second after the Big Bang. In less time than it takes to blink, the entire observable universe ballooned from smaller than a proton to a size far larger than our entire cosmic horizon. This incredible burst of growth solves the horizon problem. Why does the cosmic microwave background, the leftover heat from the Big Bang, have almost exactly the same temperature in all directions? Without inflation, there simply has not been enough time for heat to travel from one side of the sky to the other to even out. It is like walking into a room where 2 cups of coffee on opposite sides of a vast hall are the exact same temperature, but no one ever moved between them. Inflation explains this by stating that the entire visible universe was once a tiny, connected region that rapidly smoothed out before being stretched across the cosmos. The mechanism behind this is thought to be a mysterious field, dubbed the inflaton field. Think of it as an invisible energy field that permeated the infant universe, acting like a sort of anti-gravity, driving space itself to expand at a fantastic rate. Then, just as suddenly as it began, this field decayed, dumping its immense energy into creating the hot soup of particles that would become our universe. But what was this inflaton field, and what triggered its abrupt start and stop? We have no idea. Its existence is inferred solely from its dramatic effects. This leads to an even more staggering possibility. If space expanded once, could it happen elsewhere? Some models of inflation suggest it is not a one-time event but an eternal process. Our entire universe, with all its hundreds of billions of galaxies, may be just one bubble in a vast, frothing cosmic ocean, a single island in an infinite multiverse. In this view, new Big Bangs are happening all the time, each creating a separate universe with potentially different physical laws. This idea pushes the boundaries of science itself, raising a haunting question. If we are part of a multiverse, does that mean the fundamental constants of our own universe, the numbers that allow for stars, planets, and life, are not special, but simply a random roll of the dice in one favorable bubble? That lingering question of our universe's fine-tuning strikes at the very first second of its existence. The Big Bang should have been a perfectly symmetrical event, producing equal amounts of matter and antimatter. For every particle of matter, like an electron or a quark, a mirror-image antimatter particle should have been born. These opposites are drawn to each other, and when they meet, they annihilate in a flash of pure energy. If the cosmos had played by these perfectly fair rules, all of the matter and all of the antimatter would have completely wiped each other out, leaving behind a universe containing nothing but a fading sea of light. There would be no atoms, no stars, no planets, and certainly no one to ponder this mystery. Yet here we are, somehow, for every 1 billion annihilations in the early universe, a single particle of matter survived. That 1 in a billion imbalance is the only reason anything made of atoms exists today. It is the reason you exist. So what tipped the scales? Physicists call this the problem of baryogenesis, the search for the mechanism that broke the primordial symmetry. They are hunting for any tiny crack in the laws of physics, any process that treats matter and antimatter slightly differently. This is known as a violation of CP symmetry, where C stands for charge and P for parity. In simple terms, it means that antimatter might not be a perfect mirror image of matter. It might behave in a subtly different way. Scientists have found a very small CP violation in certain rare particle decays, but it is nowhere near enough to account for the overwhelming dominance of matter we see in our universe. The hunt for a larger effect is on, pursued in massive underground experiments and within the world's most powerful particle accelerator, the Large Hadron Collider. By smashing particles together at nearly the speed of light, they are recreating the conditions of the early universe, searching for exotic particles or unknown forces that could have favored matter just enough to build our entire cosmic home. The search is for the one broken rule that made all the difference. That one broken rule gave us a universe filled with matter, stars, and planets, but on all those other worlds, is anyone else out there to witness it? The sheer number of possibilities is staggering. Our galaxy alone contains hundreds of billions of stars, and many of those are now known to host their own families of planets. With so many worlds, and with the basic ingredients for life seemingly common throughout the cosmos, the universe should be a vibrant, noisy metropolis of civilizations. Yet when we listen, we hear only an immense, profound silence. This contradiction is the heart of the Fermi Paradox, famously captured by the question, where is everybody? If intelligent life is probable, its absence is deafening. One unsettling answer is the Great Filter hypothesis. This idea suggests that at some point between the emergence of life and the development of a galaxy-spanning civilization, there exists a barrier, a step so difficult that nearly every world fails to pass it. This filter could lie in our past. Perhaps the jump from non-living chemistry to the first self-replicating life is astronomically rare. Or maybe the filter is the evolution of complex multicellular organisms. If so, we are incredibly fortunate to be here at all. The more chilling possibility is that the great filter awaits us in our future. It could be that almost every advanced civilization, upon reaching a certain level of technological prowess, inevitably discovers a technology that leads to its own destruction, whether through nuclear war, engineered pandemics, or a runaway artificial intelligence. In this scenario, the silence of the cosmos is a grave warning. Other solutions are less ominous but equally strange. The zoo hypothesis proposes that advanced civilizations are aware of our existence but have chosen to isolate us, perhaps as a form of galactic conservation, or to allow our society to develop naturally without interference. We could be living in a cosmic wilderness area deliberately left uncontacted. Alternatively, the vast distances and timescales of the galaxy might mean that civilizations simply do not overlap. Others may have risen and fallen millions of years ago, their signals long since faded into nothing, leaving us alone in the ruins of their ancient empires. Or the simplest answer of all could be true. Maybe the development of complex, tool-using intelligence is not an inevitable outcome of evolution, but a bizarre fluke, a one-in-a-trillion accident that has only ever happened once right here. In a cosmos that seems so perfectly tuned for life, the greatest mystery might be why it feels so utterly, completely empty. Even in the profound emptiness, our own spacecraft can behave in unexpected ways. For decades, two robotic pioneers, Pioneer 10 and Pioneer 11, sent back data as they journeyed toward the edge of our solar system, but scientists noticed something deeply puzzling. Both spacecraft were experiencing a tiny, unexpected, and constant deceleration, a slight pull back toward the sun. This was the Pioneer anomaly, a minuscule drift that defied the known laws of gravity. It was as if an invisible hand was gently tapping the brakes on humanity's first emissaries to the stars. The effect was incredibly small, less than a billionth of the gravity we feel on Earth, but over the vast distances of space, this tiny discrepancy added up, pushing the spacecraft hundreds of thousands of miles off their predicted courses. For years, this mystery fueled intense speculation. Was it evidence of some unknown form of matter scattered throughout the solar system, subtly tugging on the probes, or was it something far more revolutionary, a sign that our understanding of gravity itself was incomplete at these immense scales? Perhaps Einstein's theory of general relativity needed a slight modification in the weak gravitational fields of deep space. The most dramatic theories suggested we were seeing the first hints of a new physics. But science has a way of finding mundane answers for seemingly magical problems. The primary suspect eventually became the spacecraft themselves. These probes are powered by the heat from radioactive decay, and that heat has to go somewhere. Engineers realized that the simple act of the spacecraft radiating heat could provide the answer. Photons of thermal radiation streaming from the warm electronics compartments would carry a tiny amount of momentum. If this radiation was not perfectly symmetrical, if just a little more heat was emitted in one direction than another, it could create a net pressure, a gentle push. For Pioneer, this push happened to be directed back toward the Sun, perfectly mimicking a slight, additional gravitational pull. After years of painstaking analysis, recreating the spacecraft's thermal properties and plumbing the depths of the old telemetry data, the consensus formed. The most likely culprit was not dark matter or new gravity, but the faint infrared glow of the probe's own power systems. The Pioneer anomaly was largely solved. Yet its legacy is profound. It stands as a testament to the incredible precision of modern astronomy, where a deviation smaller than a nanometer per second squared can trigger a decades-long scientific detective story. It reminds us that even in the void, we must account for every whisper of energy, and that the greatest mysteries are sometimes hidden in the smallest, most subtle signals. That legacy of faint signals in the void is eclipsed by one single, powerful burst that has never been explained. In the summer of 1977, a radio telescope at Ohio State University known as the Big Ear was silently scanning the sky, part of the long-running search for extraterrestrial intelligence. On August 15th, the system recorded a signal so intense and so peculiar that it defied all expectations. It was a narrowband radio burst precisely at the frequency of the hydrogen line, a wavelength many scientists considered a natural choice for interstellar communication because hydrogen is the most common element in the universe. The signal leapt in intensity, peaked for a full 72 seconds as the Earth's rotation swept the telescope's gaze across that particular point in the constellation Sagittarius, and then vanished just as abruptly. Days later, astronomer Jerry Amon was reviewing the computer printout, a long scroll of alphanumeric data. His eye caught the sequence of 6 characters, one for each of the telescope's receivers, that represented this extraordinary spike. Circling them in red pen, he wrote a single, powerful word in the margin. Wow, that original printout with its famous annotation has become a sacred relic in the quest to find other life. The signal's characteristics were exactly what scientists were looking for, a strong, artificial-seeming broadcast from a fixed point among the stars. It was not random noise, not a known natural source, and not anything from Earth, as its frequency fell within a protected radio band where terrestrial transmissions are forbidden. It was for one perfect minute the candidate everyone had been waiting for. And then it was gone. For decades, astronomers have repeatedly pointed their most powerful dishes toward that same spot, listening for a repeat, for a pattern, for anything. The silence has been absolute. The wow signal never returned. The search for a natural explanation has produced many contenders, but all have fallen short. Some suggested it was a reflection from a passing human satellite or piece of space debris, but no known object matched its timing and trajectory. Others proposed a comet, as 2 were in the general area in 1977. But comets emit broad, messy radio signals, not the sharp, focused burst that was detected. The signal remains an enigma, a one-time shout into the cosmic night that we happen to be in the right place at the right time to hear. It stands as a monument to both the promise and the profound frustration of the search. Was it a fleeting, accidental brush with an alien beacon, a cosmic lighthouse whose beam swept past us only once? Or was it a completely natural but still unknown astrophysical event, a celestial mirage we have yet to understand? The single word written on that printout captures the entire human reaction to the cosmos, a mixture of stunned discovery and the humbling, enduring mystery of what it all means. The profound silence following the wow signal leaves us confronting the mysteries much closer to home, in the frozen outskirts of our own solar system. Far beyond the orbit of Neptune lies a vast reservoir of icy worlds known as the Kuiper Belt. This is the solar system's final frontier, a cosmic junkyard filled with primordial leftovers from the birth of our planetary system. Astronomers expected this population of frozen objects to continue steadily, thinning out gradually with distance, but that is not what they found. Instead, at a distance of about 50 astronomical units from the Sun, the number of Kuiper Belt objects suddenly and dramatically plummets. It is as if you are walking along a beach where the sand gradually gets deeper, only to find a sheer, unexpected cliff dropping off into an empty ocean. This is the Kuiper Belt Cliff, and its existence defies our basic models of how the solar system formed. If the primordial disk of gas and dust from which everything formed simply ended at that point, why would it have such a sharp edge? Disks in nature tend to fade gradually, not stop abruptly. This has led to a compelling and controversial alternative explanation: the gravitational influence of an unseen planet. The hypothetical Planet 9 is theorized to be a massive world, perhaps 10 times the mass of Earth, tracing a highly elongated orbit far beyond the Kuiper Belt. The gravitational pull of such an object could act as a cosmic shepherd, its immense gravity clearing out a vast swath of space by either ejecting smaller objects or herding them into clustered, tilted orbits that we have not yet fully mapped. This would neatly explain the cliff, but the search for this phantom planet has so far come up empty, turning it into one of the most high-stakes treasure hunts in modern astronomy. Alternatively, the cliff might be a primordial relic, a frozen snapshot of the conditions in our infant solar system. Perhaps the protoplanetary disk that birthed our planets truly did have a sharp outer boundary, carved by the gravitational tides of a passing star in the Sun's birth cluster billions of years ago, or limited by the amount of material available at that great distance. This would mean the Kuiper Belt Cliff is not a dynamic feature sculpted by a hidden world, but a fossil, a lasting impression of the chaotic nursery our solar system once called home. Either possibility reveals a fundamental gap in our understanding. Is our solar system still dynamically active, hiding a giant planet in the darkness, or is the architecture of its outer reaches simply a ghost, an echo of a moment in time that has been frozen for 4.5 billion years? Our own galactic neighborhood is caught in a cosmic current we cannot fully see. The Milky Way is not drifting aimlessly through the void. Along with our entire local group of galaxies, we are racing through space at a staggering speed of over 2 million kilometers per hour, pulled by a colossal gravitational anomaly known as the Great Attractor. This mysterious focal point of gravity lies roughly 150 million light-years away, in the direction of the constellation Centaurus. But when astronomers point their telescopes toward that part of the sky, their view is blocked. The Great Attractor lies directly behind the plane of our own Milky Way, a region so choked with cosmic gas, dust, and the glare of countless stars that it is famously called the zone of avoidance. It is as if the universe placed its most compelling secret directly behind a brilliant, impenetrable wall. For decades, this was a profound blind spot in our cosmic map. We could feel the irresistible pull, but we could not see what was doing the pulling. The leading theory today suggests the Great Attractor is not a single, unimaginably dense object, but something far grander in scale. It appears to be the gravitational heart of our home supercluster, an immense cosmic structure named Laniakea, a Hawaiian word meaning immense heaven. Laniakea is a vast web of galaxies, a filamentary network spanning over 500 million light-years, and our Milky Way is just a single suburb on its outermost fringe. The pull we feel is the collective gravity of this entire structure, drawing every galaxy within its domain toward the common center of mass. Yet, even with this understanding, the mystery has not fully vanished. The sheer amount of mass required to generate such a powerful gravitational tug is immense, and the visible galaxies within Laniakea do not seem to provide enough. This implies there are still enormous concentrations of dark matter, and perhaps entire clusters of galaxies still hidden from our view behind the galactic dust of the zone of avoidance. We are like fish in a pond, feeling the current pulling us toward a waterfall we cannot see past the water's shimmering surface. The great attractor is a humbling reminder that we are passengers on a vast cosmic journey, pulled toward a destination whose full nature remains just out of sight. This cosmic current pulling us through the void is mapped against a backdrop of ancient light, but even that primordial canvas holds a strange and unsettling pattern. The cosmic microwave background is the oldest picture we have of the universe, a snapshot of the hot, dense plasma that filled the cosmos just 380,000 years after the Big Bang. According to our most fundamental cosmological principle, this radiation should be essentially the same in all directions, a perfectly random and isotropic relic of the infant universe. Yet, when scientists created exquisitely detailed maps of this faint glow, they found something they never expected. Subtle statistical fluctuations in the background temperature appear to align along a specific preferred axis, a mysterious orientation that has been nicknamed with a hint of dramatic irony, the axis of evil. The name reflects just how troubling this alignment is. It suggests that the universe has a preferred direction, a cosmic north, which directly challenges the cosmological principle itself, the core idea that the universe is homogeneous and isotropic, that it looks the same in every direction and has no special place. It is as if you were floating in the middle of a vast, featureless ocean, only to discover that all the waves are subtly tilted toward a single point on the horizon. Some interpretations of this anomaly are truly radical. Could this axis be a fossil imprint from a time before the Big Bang, a scar left by an earlier phase of the cosmos that set a preferred spin on our entire universe? Perhaps it indicates that our universe is not infinite and uniform, but has a more complex, lopsided structure on scales far larger than we can observe. The controversy surrounding this finding is immense. The scientific mainstream largely attributes the axis of evil to a combination of statistical flukes, subtle errors in how we subtract the foreground glow of our own Milky Way galaxy, or other observational biases. After all, when you are analyzing a dataset of such immense complexity, it is always possible to find patterns that look significant purely by chance. Many cosmologists believe that with more precise data from future missions, this strange axis will simply fade into the noise, yet it stubbornly persists, a faint but undeniable crack in the foundation of our standard model. It remains a topic of fierce debate precisely because it touches on something so fundamental. If the universe truly has a preferred axis, it would force us to rewrite the first chapters of our cosmic story and reconsider our most basic assumptions about the nature of reality itself. Our cosmic models are built with astonishing precision, yet one of their most fundamental predictions is wrong by a factor of 3. This is the lithium problem, a quiet but persistent crack in the story of the Big Bang. In the first few minutes of the universe, the cosmos was a nuclear fusion reactor, forging the primordial elements that would become the building blocks of everything to come. Our calculations tell us exactly how much of each element should have been created, a cosmic recipe written in the laws of physics. For the two lightest elements, hydrogen and helium, the predictions match the ancient, observed abundances in nearly pristine gas clouds with spectacular accuracy. It is one of the great triumphs of modern cosmology, but for the third lightest element, lithium-7, the numbers fail dramatically. The universe should contain about 3 times more lithium than we can actually find when we look at the oldest stars in our galaxy. These ancient stellar relics are like cosmic time capsules, their atmospheres preserving the chemical composition of the early universe, and they are all missing the same amount of lithium. So where did it go? One possibility is that our understanding of nuclear physics in that first fiery moment is incomplete. Perhaps an unknown particle, like a certain type of dark matter particle, was present in the early universe and interacted with the primordial soup, destroying lithium as it formed. Another line of thought points the finger not at the birth of the universe, but at the stars themselves. Maybe we do not fully understand the complex churning and mixing that occurs deep within stellar interiors. Lithium is a fragile element, and it is destroyed at temperatures lower than those needed to create it. It is possible that these ancient stars, over their billions of years of life, have been slowly burning away their primordial lithium in their cores, dragging the material down from their surfaces and consuming it. If our models of this process are even slightly off, we could be grossly underestimating how much lithium was originally present. This seemingly small accounting error carries immense weight. It strikes at the heart of Big Bang nucleosynthesis, the very process that created the first atoms. If we cannot accurately predict the amount of just one element, what other subtle details might our grand cosmological model be missing? The lithium problem is a quiet whisper from the dawn of time, suggesting that our story of creation, for all its successes, is not yet complete. This seemingly minor lithium deficit is a warning that our cosmic accounting can be subtly wrong, and that warning grows into a full-scale crisis when we try to pin down the most fundamental number in all of cosmology, the Hubble constant. This single figure describes how fast the universe is expanding today, the current rate at which galaxies are rushing away from us. For decades, astronomers have worked to measure it with ever greater precision, but they have now arrived at a deeply troubling contradiction. Two of our most trusted methods, each seemingly bulletproof, are giving us two different, stubbornly incompatible answers. It is as if you used two different rulers to measure the same table and got two different lengths, even though you are certain both rulers are perfectly accurate. The first method looks back to the very beginning, to the cosmic microwave background. By analyzing the subtle patterns in this ancient light, the Planck satellite could extrapolate the entire history of cosmic expansion, predicting what the Hubble constant should be today. This is a top-down approach based on our fundamental model of the universe. The other method builds from the bottom up, using the local universe as our laboratory. Astronomers observe pulsating stars called Cepheid variables and cataclysmic type, one a supernova, in relatively nearby galaxies. These objects are standard candles, meaning we know their intrinsic brightness. By measuring how bright they appear from Earth, we can calculate their exact distance. Combining this with measurements of how fast those galaxies are moving away from us gives us a direct local measurement of the expansion rate. The problem is stark. The Planck measurement from the early universe suggests an expansion rate of about 67 kilometers per second per megaparsec. But the local measurements from supernova and stars consistently give a faster rate, around 73. This gap might seem small, but given the incredible precision of these modern experiments, the discrepancy is now many times larger than the estimated margins of error. This is not a minor statistical fluke, this is the Hubble tension. Something is fundamentally wrong. Either one of our methods contains a subtle, unaccounted for error, or our standard model of cosmology is incomplete. The excitement in cosmology today is driven by this very conflict, because if it is not an error, it must be new physics. Perhaps dark energy is not constant, but has been evolving over time, strengthening in the recent cosmic past to accelerate the expansion faster than our models predicted. Or maybe dark matter possesses some strange, unknown property that changes how it interacts with the cosmos. There could even be a new, previously undetected type of neutrino or another exotic particle that was abundant in the early universe and has subtly altered the expansion history. The possibility of a systematic error is still seriously considered. Maybe our understanding of Cepheid stars is not quite perfect, or there is some unforeseen complexity in the physics of supernova. But as each year passes and more experiments confirm the divide, the case for a cosmic oversight grows stronger. This tension is more than just a number, it is a direct challenge to our story of the universe. It hints that there are chapters in the book of physics we have not even begun to read, and that the cosmos is still hiding profound secrets about its own inner workings. The Hubble tension reveals a crack in our cosmic model, but there is a deeper, more fundamental gap in our history of the universe. We have never seen the very first generation of stars. According to our theories, after the Big Bang cooled, the cosmos was a simple place, filled only with hydrogen, helium, and a trace of lithium. There were no planets, no carbon, no oxygen, no silicon for rocks. The first stars to ignite in this pristine darkness, known as population 3 stars, would have been unlike anything that exists today. Born from clouds of pure hydrogen and helium, with no heavier elements to help them cool and fragment, they would have grown to staggering sizes, behemoths hundreds of times more massive than our Sun. These cosmic titans would have lived fast and died young, burning with a ferocious blue-white intensity and consuming their nuclear fuel in just a few million years, a mere blink in cosmic time. Their deaths would have been equally spectacular, collapsing into massive black holes or exploding in violent supernova that forged the very first heavy elements, the carbon in our bodies, the oxygen we breathe, the iron in our blood. They are the mythical founders of our complex universe, the alchemists that seeded the cosmos with the ingredients for everything that followed. Yet, for all their theoretical importance, we have never conclusively found one. The hunt for these missing giants is one of the primary missions of the James Webb Space Telescope. Its powerful infrared eyes are perfectly suited to peer back to the very edge of time, searching for the unique chemical signature of a star that contains not a single atom of any metal, a beacon of pure primordial gas. So why have we not found them yet? One possibility is that they were simply too unstable. Forming from perfect, simple gas, they might have been so massive that their own intense radiation prevented them from fully collapsing, or they might have torn themselves apart before they could even begin stable fusion. Another, more likely, scenario is that their era was incredibly brief. The first stars would have formed in isolation, but their cataclysmic deaths would have polluted their surroundings with heavy elements almost immediately. The next generation of stars, population 2 stars, which we do see in the ancient globular clusters of our galaxy, already contain a tiny sprinkle of these heavier elements. This suggests the transition from the first pure generation to the second polluted one was swift. It is possible that every single population 3 star lived, died, and vanished within the first few 100 million years of the universe, their light now stretched into faint infrared whispers by the expansion of space. Or perhaps we are looking for the wrong thing. Maybe the first stars were not all solitary giants but formed in clusters, their collective light too diffuse for our current telescopes to pick out as individual points. Finding even one of these primordial giants would be like discovering the first chapter of a cosmic epic, a chapter we have only ever been able to imagine. Their absence is a silent question mark hanging over the universe's very first dawn. These vast, silent stretches of the cosmos are not just empty space, they are profound absences. Scattered across the universe are enormous regions known as cosmic voids, colossal bubbles of near-nothingness that can stretch for hundreds of millions of light years. They are the empty rooms in the mansion of the universe, and their existence poses a direct challenge to our understanding of how everything formed. The most famous of these is the Boötes void, a spherical chasm so immense that our entire local group of galaxies would be just a tiny speck inside it. If the Milky Way were at its center, we would not have seen another galaxy until the 1960s. The void is not completely barren, but it contains only a few dozen galaxies where a region of that size should hold thousands. The mystery is not just that these voids exist, but why they are so starkly empty. According to our models of cosmic evolution, the gravitational tug of dark matter should have pulled at least some galaxies into these regions over billions of years. Their profound emptiness suggests that dark matter itself might be arranged in a vast cosmic web, with the voids representing the empty spaces in the weave, where the gravitational scaffolding is too weak to collect even the invisible stuff, let alone the visible galaxies. So what happens inside one of these cosmic deserts? The environment would be profoundly alien. With so few neighboring galaxies, the night sky on a planet inside a void would be almost black, punctuated by just a handful of faint, lonely island universes. Yet it might not be completely dark. Some theories suggest that vast numbers of isolated stars, flung free from their home galaxies during cosmic collisions, could be drifting through the void, solitary beacons in an endless night. The dynamics of dark energy are also thought to play out differently here. In the crowded galaxy clusters, gravity's pull is strong, locally resisting the relentless push of dark energy. But inside a void where gravity's grip is weakest, dark energy may reign supreme, accelerating the expansion of this empty space itself, potentially making the voids grow even larger and emptier over time. These cosmic vacuums are not just passive holes, they are active players in the evolution of the universe, their growing emptiness helping to tear the cosmic web apart. Far out in the cosmic voids where emptiness reigns, we find the ultimate paradox in the darkest objects of all. Stephen Hawking made a discovery that shook the foundations of physics, proving that even black holes are not truly black. They glow with a faint heat now known as Hawking radiation. This is not light escaping from within the event horizon, the point of no return, but a subtle quantum effect happening right at its edge. According to quantum theory, empty space is not empty. Pairs of virtual particles, one with positive energy and one with negative energy, constantly flicker into and out of existence. When this happens at the precipice of a black hole, one particle can fall in while the other escapes, stealing a tiny amount of the black hole's mass and carrying it away as radiation. Over unimaginable eons, this process causes the black hole to slowly shrink and ultimately evaporate completely. This is where the paradox ignites. What happens to all the information about the things that fell in? When a book is burned, its information is not truly lost, just transformed into a chaotic state of smoke and ash. In principle, a being with perfect knowledge could reverse the process and reconstruct the book. Quantum mechanics insists that information can never be destroyed, only scrambled. But general relativity paints a bleaker picture for a black hole. It describes the interior as a place where the laws of physics break down, where all the intricate details of a star, a planet, or a person are crushed into a single point of infinite density, a singularity. If the black hole then evaporates into a featureless cloud of Hawking radiation, that information appears to be erased from the universe forever. This is the black hole information paradox, a direct conflict between our two most successful theories of reality. So where does the information go? One mind-bending solution is the holographic principle. It suggests that all the information about what fell into the black hole is not lost inside, but is instead encoded on its two-dimensional surface, the event horizon, like a cosmic fingerprint. The three-dimensional interior we imagine is just a projection of that data. Much like a hologram on your credit card is a three-dimensional image projected from a two-dimensional surface. When the black hole evaporates, this information is slowly and chaotically released back into the universe through the Hawking radiation. Another, more violent idea is the firewall hypothesis. It proposes that the event horizon is not a smooth, empty space as relativity suggests, but a blazing wall of high-energy particles. Anything crossing it would be instantly incinerated. This firewall would protect the laws of quantum mechanics by ensuring information never actually enters the black hole, but it completely shatters Einstein's picture of someone falling in smoothly, unaware of their fate. Both of these solutions force us to abandon a cherished principle, revealing that our understanding of spacetime itself is likely incomplete. The fate of a single bit of information inside a black hole may hold the key to a unified theory of quantum gravity, a theory of everything. It is a cosmic puzzle where the stakes could not be higher, for the answer will redefine our very concept of reality. While black holes grapple with the fate of information, our own planet is constantly bombarded by cosmic messengers carrying secrets of their own. Ultra-high energy cosmic rays are the universe's most powerful natural particle accelerators. These are not rays of light, but individual subatomic particles, often a single proton or atomic nucleus, traveling through space at nearly the speed of light. When one of these cosmic bullets strikes the top of Earth's atmosphere, it unleashes an avalanche of secondary particles, a vast shower that can spread over dozens of square kilometers by the time it reaches the ground. The energy packed into that single particle is staggering, millions of times greater than what we can achieve in our most powerful human-made colliders, like the Large Hadron Collider. It is the energy of a well-thrown baseball concentrated into a single, fundamental piece of an atom. The sheer existence of such particles is a profound mystery. What cosmic engine in the universe can possibly hurl a tiny piece of matter with such unimaginable force? The challenge of answering that question is immense because these particles are electrically charged. As they travel across the cosmos, the weak but pervasive magnetic fields that thread through interstellar and intergalactic space act like a hall of mirrors, bending and twisting their path. By the time a cosmic ray reaches us, its trajectory is a hopelessly scrambled mess. We can see the spectacular fireworks show in our atmosphere, but we cannot simply look back along a straight line to find its source. It is like trying to find the origin of a leaf carried by a winding river long after the current has swept it away. So where could they come from? The suspects are the most violent and energetic phenomena in the cosmos. Active galactic nuclei, the supermassive black holes at the hearts of galaxies, are prime candidates. As these black holes devour vast amounts of material, they can create jets of plasma shooting out at near light speed, which could potentially accelerate particles to these extreme energies. Cataclysmic gamma-ray bursts, the birth cries of black holes from the deaths of massive stars or the mergers of neutron stars, are another potential source, their immense explosive power acting as a natural particle cannon. Some physicists even speculate about more exotic origins, like the decay of super-heavy, as yet undiscovered, particles from the early universe or defects in the very fabric of spacetime. To solve this puzzle, scientists have built enormous detective agencies on the ground. The Pierre Auger Observatory in Argentina is a prime example, a sprawling array of 1,600 water tanks spread over 3,000 square kilometers, an area larger than Rhode Island, alongside telescopes that watch for the faint ultraviolet glow of the air showers. By combining the data from thousands of these detections, the observatory slowly pieces together the energy and the rough direction of the incoming cosmic rays. The hunt is painstakingly slow, a statistical game of connecting dots across the galaxy and beyond. Every ultra-high energy particle that strikes our atmosphere is a postcard from a cosmic monster, but the address has been blurred by the magnetic winds of deep space. Unraveling their origin is not just about finding a source, it is about understanding the ultimate limits of nature's power and witnessing the final, furious moments of the universe's most extreme events. That faint whisper of cosmic rays is joined by a deeper vibration, a ringing in the very fabric of spacetime itself. These are gravitational waves, ripples that travel at the speed of light, stretching and squeezing everything in their path. We have already detected the loud, crashing waves from the mergers of stellar mass black holes, but beneath these distinct events lies something far more subtle and pervasive. It is a constant, low-frequency hum, a cosmic chorus known as the stochastic gravitational wave background. Imagine standing in a forest and hearing a single tree fall. That is a black hole merger. Now imagine hearing the collective rustle of every leaf in the entire forest at once. A sound so vast it becomes a single, resonant tone. That is the background. This hum is thought to be generated by countless pairs of supermassive black holes, each millions or even billions of times the mass of our Sun, orbiting each other in the hearts of distant galaxies. As these cosmic giants spiral inward over millions of years, they pump immense energy into space-time, creating a sea of overlapping waves that washes through the entire universe. But how do you listen to a hum that is quieter than the faintest whisper? You use the most precise metronomes in the cosmos, pulsars. These are the rapidly spinning corpses of massive stars, beaming radio waves with the regularity of atomic clocks. Scientists use networks of these pulsars as a galaxy-spanning telescope. They measure the tiny, correlated shifts in the arrival time of these pulses, looking for the telltale stretching of space-time as a gravitational wave passes between us and the pulsar. It is an experiment of almost unbelievable precision, detecting distortions in space-time smaller than the nucleus of an atom across light-years of distance. Unlocking this background hum would open an entirely new window onto the cosmos. It would reveal the population and history of the most monstrous objects in existence, showing us how often galaxies merge and how their central black holes dance together. The characteristics of the hum, its pitch and volume, could even tell us about the universe's properties in its earliest moments, probing a time before the first stars, when space-time itself was a turbulent ocean. This is not just about listening to black holes, it is about hearing the universe breathe and deciphering the secrets carried on that primordial rhythm. That low cosmic hum is a reminder of how much we learn from what passes by, but in 2017, something passed through our solar system that was unlike anything we had ever seen. It was the first visitor from another star, a small, fast-moving object detected by the Pan-STARRS telescope in Hawaii, and it was given a name that reflected its historic nature, Oumuamua, a Hawaiian word for scout. From the moment it was spotted, it was clear this was no ordinary comet or asteroid. It was already on its way out of the solar system, a fleeting glimpse of a traveler from the vast interstellar deep. The data revealed one strange characteristic after another. Its shape was the most extreme we have ever observed, a pancake or a cigar-shaped object perhaps 10 times as long as it was wide, tumbling chaotically through space. This alone was bizarre, as most solar system objects are far more rounded. Then came the real head-scratcher. As it traveled away from the Sun, astronomers tracking its path noticed a slight but definite non-gravitational acceleration. Its speed was changing in a way that could not be explained by the gravity of the Sun or planets alone. For a normal comet, this is a common effect caused by outgassing. As the Sun heats the icy surface, jets of gas erupt like tiny engines pushing the comet along. But Oumuamua showed no visible coma, the fuzzy cloud of gas and dust that always surrounds an active comet. It appeared completely dark and inert, a silent, solid rock. Yet something was making it speed up. This single observation ignited a firestorm of debate that continues to this day. The scientific mainstream scrambled for natural explanations. Could it be a very old, crusty comet whose outgassing was primarily made of pure hydrogen? This gas would be invisible to our telescopes, but could provide just enough of a push. Another compelling theory suggested it was a chunk of solid nitrogen, a cosmic iceberg that had been chipped off the surface of a Pluto-like world in another star system. As the sun warmed its surface, nitrogen would sublimate directly from solid to gas, providing the thrust without creating a dusty coma. Both of these are fascinating possibilities, painting a picture of a universe filled with exotic, unseen planetary debris. Yet the object's peculiar shape and the precise nature of its acceleration led some scientists, like Harvard's Avi Loeb, to propose a more speculative idea. Could Oumuamua have been an artificial object, a piece of advanced alien technology, perhaps a light sail using the pressure of starlight for propulsion? This was not the preferred explanation, but it highlighted a fundamental truth about this encounter. We had one chance, one set of limited, ambiguous data on an object that is now forever beyond our reach. The debate over Oumuamua is a masterclass in how science grapples with the truly unprecedented. It forces us to confront the limits of our knowledge and the challenge of interpreting a brief, mysterious signal from the dark. Was it a nitrogen iceberg, a strange asteroid, or something else entirely? We may never know for sure, but its visit taught us one undeniable lesson. The universe is capable of producing wonders that defy our expectations, and our cosmic neighborhood is far more dynamic and strange than we ever imagined. This shadowy force dictating our cosmic fate is described by a single, crucial number known as its equation of state. Think of this number as the personality of dark energy, a value that tells us whether its repulsive strength will remain constant, weaken, or grow more powerful over time. Our ultimate destiny hinges on this one elusive digit. The most widely accepted scenario is the Big Freeze or heat death. If dark energy is a true cosmological constant, its push will remain steady. The universe will expand forever, its acceleration gradually isolating every structure. First, galaxy clusters will be pulled apart, their members drifting beyond each other's cosmic horizons. Then, individual galaxies will be stripped of their stars. Over trillions of years, stars will burn out one by one until the last red dwarf flickers and dies. The universe will become a cold, ever-thinning soup of scattered particles and black holes, which themselves will eventually evaporate via Hawking radiation. All activity, all heat, all light will cease, reaching a state of maximum entropy where nothing ever happens again. But what if dark energy is not constant? What if it decays over time? This opens the door to a far more dramatic ending, the Big Crunch. If the repulsive force weakens enough, gravity could finally reassert its dominion. The expansion of the universe would slow, halt, and then reverse. Every galaxy would begin rushing toward every other galaxy. The cosmic background temperature would rise as the universe collapses back in on itself. Space itself would heat up, first to the temperature of stars, then to that of the primordial fireball. Eventually, all matter and energy would be compressed into an ultra-hot, ultra-dense singularity, a mirror image of the Big Bang, perhaps even giving birth to a new universe in an endless cycle of birth and death. The most violent possibility, however, is the Big Rip. If the equation of state reveals that dark energy intensifies over time, its repulsive force would grow without bound. First, it would overcome the gravity holding galaxy clusters together, tearing them asunder. Then, it would rip apart individual galaxies. As the force strengthens, it would overcome the forces holding stars and planets together. In the final, terrifying moments, the expansion would become so violently fast that it would overcome the electromagnetic force holding your body together, and then the nuclear forces holding atoms themselves intact. The very fabric of space-time would be shredded. The entire cosmos would end not with a slow fading, but with a single, catastrophic instant of disintegration. So how do we determine which of these fates awaits us? The answer lies in measuring the universe's expansion history with even greater precision. New telescopes like the Vera C. Rubin Observatory and the Nancy Grace Roman Space Telescope are designed to map billions of galaxies and thousands of supernovae. By tracking how the expansion rate has changed over cosmic time, they will measure the equation of state of dark energy with unprecedented accuracy. We are, in effect, taking the cosmic pulse, trying to diagnose the long-term health of the universe itself. The mystery of our ultimate end is not a question of if, but of how. Will it be an eternal, silent freeze, a fiery collapse, or a final, absolute rip? The answer is written in the dark, and we are only just learning how to read it. The ultimate fate of the cosmos hinges on forces we can barely measure, but what about the very stage on which this drama plays out? Space-time itself, the smooth, continuous fabric described by Einstein's general relativity, harbors a deep and fundamental secret. On the grand scale of planets and galaxies, it appears as a gently curving sheet, warped by mass and energy. But when we peer into the subatomic realm, the quantum world tells a different story entirely. Here, everything is granular and jittery, a sea of discrete particles and fuzzy probabilities. This creates a monumental conflict at the heart of physics. Our two most powerful theories, one for the immensely large and one for the incredibly small, are fundamentally incompatible. To describe the most extreme places in the universe, like the infinitely dense singularity at the center of a black hole or the very first moment of the Big Bang, we desperately need a theory that can marry these two views. We need a theory of quantum gravity. Without it, our equations simply break down, yielding meaningless answers of infinity where physical law ceases to exist. The quest for this unified theory has spawned several brilliant yet unproven candidates. String theory proposes that the fundamental constituents of reality are not point-like particles, but unimaginably tiny, vibrating loops of energy. The different vibrational patterns of these strings would give rise to every particle and force in nature, weaving gravity into the quantum tapestry. It is a beautiful and mathematically elegant idea, but it comes with a staggering implication: the requirement of extra-spatial dimensions, curled up into sizes so small we could never perceive them. The other leading contender, loop quantum gravity, takes a different path. It suggests that space-time itself is not smooth, but is woven from a network of finite, discrete loops, a fabric of tiny, interwoven threads. In this view, there is no such thing as an infinitely small point. There is only a smallest possible unit of space, a quantum of volume. This would prevent the formation of true singularities, replacing them with a supremely dense but finite state of matter. The greatest challenge for both of these theories, and for any theory of quantum gravity, is the sheer difficulty of testing them. The energy levels required to probe these tiny scales are far beyond anything our particle colliders can ever achieve. We are left searching for indirect clues, subtle imprints that these theories might have left on the cosmic microwave background, or in the faint ringing of gravitational waves from the dawn of time. We are trying to hear the whisper of the universe's smallest structures by listening to the echoes of its largest explosions. The quantum nature of space-time remains one of the most profound and elusive puzzles, a mystery that lies at the very boundary between our current understanding and a future, deeper truth. Amid the slow, cosmic rhythms of dark energy and gravitational waves, the universe also produces flashes of violence so brief you could miss them in the blink of an eye. These are fast radio bursts, or FRB, intense blasts of radio waves that travel for billions of years across the cosmos, only to expend their entire energy in a few milliseconds. In that thousandth of a second, a single burst can release more energy than our sun puts out over 3 entire days. The sheer power is staggering, but the real puzzle is what, or who, is generating these cosmic screams. The leading suspect is a type of stellar corpse known as a magnetar. Imagine the core of a massive star, collapsed into a city-sized ball, but possessing a magnetic field so powerful it would erase every credit card on Earth from halfway across the solar system. These magnets on steroids are thought to experience starquakes, sudden fractures in their rigid crusts that could unleash titanic shocks. rippling through the surrounding space and igniting a firestorm of radio waves. Yet, the mystery deepens with a specific, peculiar subset of these events, the repeaters. While most FRBs are one-off cataclysms, a growing number of sources have been caught firing off multiple bursts, sometimes sporadically, sometimes in frantic, predictable patterns. This repetition is difficult to reconcile with a single, destructive event like a starquake or a merger. It suggests a source that can survive its own outburst, an engine that can fire again and again. This has inevitably led to more speculative ideas. Could they be produced by cosmic strings, hypothetical defects in the fabric of space-time left over from the Big Bang, vibrating like snapped guitar strings? Or, in a far less likely but captivating thought, could the precise, energetic nature of these signals be a signature of an advanced civilization, perhaps using powerful transmitters to propel light sails across interstellar distances? While the scientific consensus strongly favors natural, if extreme, astrophysics, the very discussion highlights how truly enigmatic these signals are. New telescopes like the Canadian Hydrogen Intensity Mapping Experiment, CHIME, are now scanning the entire northern sky daily, uncovering dozens of new FRBs every month. Each new detection is another data point, another clue in a cosmic conspiracy that is rapidly unfolding. We are living in the golden age of FRB discovery, where a mystery that was once a rare curiosity is now becoming a common, yet no less profound, feature of our dynamic and violent universe. The cosmic dawn did not arrive gently. After the primordial fireball faded and the universe cooled into darkness, it entered a period known as the Cosmic Dark Ages. For millions of years, space was filled with a thick, opaque fog of neutral hydrogen gas, a featureless sea that absorbed any light trying to travel through it. The end of this universal night is the epoch of reionization, a dramatic transformation that burned away the fog and cleared the skies for light to travel freely. But how did this happen, and what were the cosmic torches that lit this great fire? The leading suspects are the first stars and galaxies. As these brilliant objects ignited, they flooded the cosmos with intense ultraviolet radiation, stripping electrons from the neutral hydrogen atoms and turning the fog into a transparent, ionized plasma. This was the moment the universe became recognizable, the moment the lights truly came on. Yet the chronology of this event is a deep puzzle. Did reionization happen quickly, a sudden blaze ignited by the first monstrously large stars? Or was it a slow, gradual process driven by the collective output of countless smaller, early galaxies? The timeline is crucial because it tells us about the nature of those first luminous objects and how they assembled into the cosmic web. We know reionization was largely complete by the time the universe was about 1 billion years old, but its precise beginning, duration, and primary drivers remain hotly debated. Were brilliant quasars powered by voracious supermassive black holes major contributors, or did the faint, numerous dwarf galaxies provide the bulk of the ionizing photons? This is where the James Webb Space Telescope becomes our ultimate time machine. Its powerful infrared instruments are designed to peer directly into this era, to see the very first galaxies as they were emerging from the gloom. By studying their numbers, their brightness, and the specific signatures of their light, Webb is gathering the forensic evidence needed to solve this mystery. It is measuring how quickly the hydrogen fog cleared in different regions and at different times, piecing together a map of this cosmic revolution. The answers will reveal the true architects of the clear, transparent universe we inhabit today, showing us how the first sparks of starlight managed to set the entire cosmos ablaze. This fine-tuning of the universe extends all the way down to the very particles that make us up. Why is gravity so unimaginably weaker than all the other forces? The electromagnetic force that holds atoms together is stronger than gravity by a factor of 1 followed by 40 zeros. To understand this bizarre imbalance, physicists look at the energy scales involved. The natural energy level where gravity should become as strong as the other forces is called the Planck scale, a realm of such intense energy that it only existed an instant after the Big Bang. Yet the particles we know and observe, like the Higgs boson that gives other particles their mass, exist at energy levels trillions upon trillions of times lower. This is the hierarchy problem, the puzzle of why there is such a vast and seemingly unnatural gap between the gravity scale and the particle scale. It is as if the fundamental laws of physics have been set with two different rulers, one for the immense power of gravity's origin and another, infinitely smaller one, for the world we actually inhabit. Without some protective mechanism, the intense quantum fluctuations at the Planck scale should have dragged the mass of the Higgs boson up to that colossal level, making it so heavy that atoms could never have formed and the universe would be a lifeless, featureless void. Something must be shielding our familiar world from this underlying chaos. One of the most elegant proposed solutions is supersymmetry. This theory posits that every known particle has a hidden, super-heavy twin partner. For every electron, there would be a selectron, for every quark, a squark. The magic of this idea is that the quantum contributions from these superpartners would perfectly cancel out the destabilizing effects from the Planck scale, protecting the light mass of the Higgs and solving the hierarchy problem with beautiful mathematical symmetry. The catch is that we have never detected a single one of these supersymmetric particles, despite searching for them in our most powerful colliders. Another mind-bending solution involves the very fabric of space. Perhaps gravity only appears weak because it is not confined to our three-dimensional world like the other forces are. In theories with extra-spatial dimensions, gravity could be leaking out into these unseen realms, its strength diluted across a higher dimensional landscape. In this view, the Planck scale is not truly high. It only seems that way because we are blind to the full, multidimensional picture. These are not just abstract mathematical games. The answer to the hierarchy problem dictates what we can hope to discover next. It tells us whether we should expect to find a whole new zoo of particles at the next energy frontier, or if the secrets of gravity lie hidden in the geometry of the cosmos itself. This particle-level mystery is a direct bridge to the universe's first moments, a clue written into the mass of a single type of particle about the ultimate unity or disunity of nature's forces. Our maps of the cosmic web are missing something profound. According to our most sophisticated computer simulations of the universe, giant galaxy clusters should act as powerful natural telescopes. Their immense gravity, dominated by dark matter, should warp the fabric of spacetime so severely that light from distant background galaxies is stretched and twisted into long, thin, luminous arcs. These gravitational arcs should be a common sight, beautiful smears of light encircling the hearts of massive clusters. Yet when we point our telescopes at the real sky, we find far fewer of these giant arcs than our models predict. It is a quiet but significant mismatch, a cosmic census that does not add up. This puzzling absence suggests there might be a fundamental flaw in our understanding of dark matter itself. The standard model assumes dark matter is cold, meaning its particles move sluggishly, allowing it to clump easily into the dense cores that power strong gravitational lensing. But if dark matter were slightly warmer, if its particles were moving at a fraction of the speed of light, they would resist clumping on the smallest scales. This warmth would smooth out the central densities of galaxy clusters, making their gravitational lenses less potent and producing fewer of the dramatic, thin arcs we expect to see. The evidence for warmer dark matter is still tentative, but it points toward a universe where the invisible scaffolding is more dynamic and less lumpy than we thought. Alternatively, dark matter might not be completely dark. What if these unknown particles can interact with each other through some unknown force, a dark version of electromagnetism? Such interactions would create a form of pressure, preventing the dark matter from collapsing into the ultra-dense, pin-sharp peaks needed to forge the most extreme arcs. The missing arcs are more than just a statistical curiosity. They are a ghostly fingerprint. They hint at the true nature of the universe's dominant matter, suggesting it is not the simple, cold, and passive substance of our standard model, but something with more character, something with properties we are only beginning to sense. This cosmic discrepancy holds a mirror to our ignorance, showing us that even the dark, unseen majority of the cosmos may have a hidden complexity we have yet to fully unravel. This staggering mismatch between prediction and reality is the cosmological constant problem, and it stands as perhaps the single greatest failure of theoretical physics. We have two pillars of modern science, quantum field theory and general relativity, and when we use them to calculate the energy density of empty space, the vacuum itself, they give us a number of such immense proportions it is almost meaningless. The quantum vacuum is not a true nothingness. It is a seething, bubbling sea of virtual particles flickering in and out of existence. This quantum jitter should fill every cubic centimeter of space with a tremendous repulsive energy, driving the expansion of the universe at a ferocious, catastrophic rate. The calculated value is a 1 followed by 120 zeros times larger than the tiny, gentle acceleration we actually observe from dark energy. This is an error margin so vast it is like predicting that a single breath of air should have the explosive force of 1 trillion thermonuclear bombs. The observed cosmological constant, the value that describes the actual push of dark energy, is not just a little off, it is infinitesimally small, a whisper when our theories scream. The true mystery is not just why the number is so small, but why it is not precisely zero. A perfect zero would be strange, but perhaps easier to explain with some elegant symmetry in the laws of physics. Instead, we have a value that is just enough to dominate the cosmos today, a tiny, non-zero nudge that is shaping the ultimate fate of everything. This problem likely cannot be solved by tweaking our existing theories. It demands a revolution, a fundamental new understanding of how quantum mechanics and gravity intertwine at the most fundamental level. Perhaps the vacuum energy is not constant, but has dynamically relaxed to its current value over cosmic history. Or maybe our concept of empty space is fundamentally wrong, and the contributions from the quantum foam somehow cancel each other out in a way we cannot yet comprehend. Solving this problem is not an academic exercise, it is a direct path to a deeper theory of quantum gravity, a theory that would finally explain why the void has just enough weight to steer the destiny of the entire cosmos. From the ghostly pull of dark matter to the faint hum of gravitational waves, these 25 mysteries paint a portrait of a cosmos far stranger than we ever dreamed. Each one is a frontier, a question mark on the map of human knowledge, reminding us that our understanding is still a tiny island in a vast ocean of the unknown. The universe is not just expanding in size, its very expansion seems to be generating new puzzles faster than we can solve the old ones. Every answered question peels back a layer, only to reveal deeper, more fundamental riddles waiting beneath. This is the great adventure of science, a never-ending journey into the dark, armed only with curiosity and the light of reason. So keep looking up and keep wondering. Follow the breathtaking new data from telescopes like James Webb and Roman as they turn these cosmic whispers into shouts of discovery. The story of the universe is still being written, and we all have a front row seat. Tell us in the comments which of these profound mysteries captures your imagination the most.